All right, so in this video, we're going to be looking at graphing systems of inequalities. And so there's going to be two kinds of inequalities we're going to be dealing with. One is going to involve vertical and horizontal lines where there's just one variable. Out of context, this might seem like maybe we should graph them on just a number line, but we're going to combine these with the two-dimensional inequalities where there are two explicit variables. And we're going to then need to graph these on a plane. So we're going to look at what these look like when you graph them on a two-dimensional space instead of just the one-dimensional number line, in addition to looking at the cases where we have two variables in the inequality explicitly. And then we also have to deal with the fact that in some of our inequalities, we'll have less than or equal to or greater than or equal to signs that do contain, so these less than or equal, the equality component versus the less than or greater than where there are no equal signs. These are going to be represented differently on our graphs. And so we're going to have to take note of those. Although the procedure for most of it is going to be quite similar. So let's start with graphing a vertical line. So a vertical line on a graph is going to be x equals a constant. And so when we're dealing with inequalities that involve x less than a, x less than a constant, or x less than or equal to a, x greater than or equal to a, or x greater than a, all of these are going to be very similarly graphed. In our specific example, we're going to look at x greater than or equal to 3. So the first thing that we're going to do is we're going to draw the boundary, which is x equals 3. So that's going to be a vertical line at x equals 3. And then the greater than sign means that we're going to graph to the right of it. We're going to shade that region to the right of it. That's going to represent all the values of x that satisfy our inequality where x is greater than 3. Now notice we're also shading all of the y regions because they're still having an x component where x is greater than 3. So there's no restriction on the y values at all. It's just that we want our x to be greater than or equal to 3. Now, if we were dealing with strictly x greater than 3 instead of x greater than or equal to 3, then the only difference here would be that we would make this line at x equals 3 dotted to indicate that it would not be included in the set. Whereas when we draw it with a solid line, we're indicating that it should be included in the set. Now let's look at a horizontal line. Horizontal lines are going to be very similar, except they're going to contain the y variable. So for example, y less than or equal to a constant, y greater than or equal to a constant, y less than a constant, or y greater than a constant. So let's look at the specific case of y less than or equal to 2. So we're going to first begin by drawing the line y equals 2, and we're going to draw that line regardless of whether it's y less than 2 or y less than or equal to 2. And then we're going to shade on the side of the line that represents y values smaller than 2, which would be below the line. So above the line would be greater than, below the line would be less than. And we leave the line solid because this inequality does contain an equal sign. If it was strictly less than, then we would make this line dotted. Now let's consider the case where we have two variables in our inequality. Now the boundary is not going to represent a horizontal or vertical line, it's going to represent some sort of slanted line. So what we can do is we can plot the intercepts or plot 2 points on the line and then connect the dots to draw our line. So in this example, our equation is solved for y. We want y to be less than or equal to 3x plus 1. So first, always draw the line. So we're going to start with an intercept of 0, 1. So that's going to be here. And then our second point, we're just going to put in a value. If we put in x equals 1, for instance, we get the point 1, 4. So when we go up to 1, we cross through the point 4, and then we connect the dots. Since this is less than or equal to, we're going to leave the line solid. If this was strictly less than, then we would make this a dotted line. Now, from there, we need to determine what side of the line we want to shade on. since this is solved for y, this is actually quite straightforward. Y less than the line would mean that you need to be underneath the line, whereas y greater than the line would mean you need to be above the line. So since this is y less than, we're going to shade for the y values that are below the line. Now, this is a little bit more complicated if the equations are in standard form. So here we have both x and y on the same side of the equation. So one option, of course, is to solve for y, but we can work with it in this form. Now, in this case, this form makes it easy to find the two intercepts. So if I let x equal to 0, then I'm going to get an intercept of 0, -3, which would be down here. And when I let y equal to 0, then I get 4, 0 from my other intercept, which would be here, and then I can connect the dots. Now, the question here is that which side of the line am I shading on? So the way that we usually do this for these kinds of problems is we choose a point where we know it's clearly on one side of the line or the other, and then we see if it satisfies the inequality if we plug it in. So typically what we do is we choose the origin if the line is not on the origin. So for instance, if I choose 0, 0, and I put that into my inequality, I end up with zeros all on this side, and 0 is indeed less than 12. That means that that origin point is on the side where the inequality should be shaded, and so we shade on every point on that side of the graph. Now, if this inequality turned out to be false, then we would shade on the side of the graph that did not contain the origin. So if this had been a greater than 12, then 0 is not greater than or equal to 12, and so we would have shaded on the opposite side of the line. Now, sometimes we get lines that go through the origin, such as 2x plus y is less than or equal to 0. So we start out by still drawing the graph in the same way we would have otherwise. We try to find 2 points on the line. In this case, it's going to go through 0, 0. So if I pick one coordinate to be 0, that forces the other coordinate to be 0 if I'm looking at 2x plus y equals 0, which is the boundary. Then I just need to pick another point on the line. So remember, when you're solving for points on the line, you're solving the equality version of this equation. So if I use x equals 1, and I plug that into the equation, which is the boundary, I end up with y is equal to -2. So I can plot this here, and then I have another point I plot there, and then I can connect the dots. Now, our test point that we used in the previous example was the origin, and this line goes through the origin. So of course it's on the boundary. So especially with the equality, it's going to satisfy the boundary line. So that's not going to be very helpful. So instead we have to pick a different point. Now, what I usually like to do is I like to pick a point that is somewhere on one of the x-axes, because then I clearly know which side of the line that it's on. It's not actually on the line. Sometimes if you pick a random point in the middle, it's not always entirely clear. Am I on the right side of the line or the left side of the line? So I always like to pick a point that's on the origin, that's clearly away from the line, and then on one of the axes. So it's clearly away from the line and very easy to tell which side of the line am I on. So here I'm going to pick the point 2, 0. And if I plug that into my inequality, I end up with 4 is less than or equal to 0. 4 is not less than or equal to 0. That's not true. That's false. And so that means that I don't want to shade on the line, on the side of the line that has the point 2, 0, my test point. Instead, I want to shade on the opposite side. So 2, 0 is false. That means every point on that side of the line is false. Now, again, the main difference between inequalities that contain equal signs and ones that don't contain equal signs, the main thing is the way that we represent the line on the graph. Otherwise, it's exactly the same procedure. So in this case, if I had, as we saw in a previous example, 3x minus 4y is strictly less than 12, as opposed to less than or equal to 12. The only difference between this solution and the previous solution is that I would represent the line that represents that boundary as dotted. And this dashed line is going to tell me that that's not actually in the solution. Whereas when the line is solid, I'm saying that that line, the boundary line, is part of the solution. You would still determine which side of the line you're shading on by selecting a test point, and with exactly the same procedure that we used before. Now, you can also graph these in the calculator, but there are some limitations. So you can't really put vertical lines into the calculator by themselves. So it doesn't like to, I mean, there are ways to draw vertical lines on the graph, but you can't really do vertical lines with inequalities. So I will sometimes just use the boundary of the window to try to represent this side of the line or that side of the line, and just display the part of the graph where the inequality is satisfied. But that is one limitation, is that it doesn't do non-functions. The calculator cannot distinguish between inequalities with and without equal signs. So it's going to draw the boundary lines exactly the same way in either case. It's only going to be able to tell you which side to shade on. And then in order to put them into the calculator, all equations have to be solved for y. In our example where we had 3x minus 4y less than or equal to 12, you do have to be careful when you divide out that -4, you have to remember to flip your inequality, or you're going to be graphing on the wrong side of the line. So let's walk through some of our examples and see how they come out in the calculator. Now, if it's already solved for y, then you go to your y equals screen and you simply put in on the regular plot screen 3x plus 1. But then in order to do the shading, you're going to scroll to the left until the cursor is sitting on this line that's in front of the y1. Now, when you get there, the line will be blinking on and off. And if you hit enter, you can scroll through the different line options. So if you hit enter once, it will make the line a little thicker. If you hit it a second time, you'll get this thing that looks like an upper triangle. The upper triangle represents the greater than representation, and or greater than or equal to, and if you hit enter again, then this will become the lower triangle, which represents the less than or equal to. And this is the condition we want because this is y is less than 3x plus 1. And from here, you hit graph, and this is what it's going to look like on your standard window. And we can compare this graph to the graph that we drew by hand, and it is shaded under the line. So this is similar to what we had before. And this is the example of the graph from earlier. So it is doing the exact same thing. Now, to do the example where x and y are on both sides of the equation, this is where we have to be super careful. So, and I'll do the less than 12 as opposed to the less than or equal to 12. So what you're going to do is you're going to first put the 3x on the other side, and then you're going to need to divide out the -4. But notice that when you divide out the -4, you have to flip the inequality. So when we put this in the calculator, you don't have to simplify your expression. You can leave it like this, but the inequality did flip over. And so when we go to plot this, we need to make sure the upper triangle is the one that is being selected here. Now, if you've used the less than and you scroll back to the left in order to change this, you're going to have to go through the entire cycle of all the other graphing options before it'll come back to the upper triangle again. It's always a good idea to test with the test point by hand just to make sure that you didn't mess up the inequality, that you're graphing on the correct side of the line. But again, when you hit graph, this is going to be your graph, and this does correspond to the graph that we had earlier. But again, this line that they're drawing doesn't distinguish between the equality case and the inequality case. So you will still have to do that yourself if you try to transfer this, for instance, to your test paper or your homework paper. Now, we can also think about systems of inequalities. If we have two inequalities that we need to satisfy at the same time, we could, in principle, have both and conditions and or conditions. So if you have a system like this, generally assume it is an and condition. If it's an or condition, then generally they will state that that is an or condition. But if there's no statement, then you should assume that it's an and condition. So the way this is going to work is essentially we're going to layer two problems on top of each other. We're going to draw both of the lines, and then we're going to try to find out where both of these inequalities are satisfied. So if we start with the line, we're going to draw the line y equals negative x. That's this blue line right here that goes through the origin. And then the second equation we have is 3x minus y is equal to negative 6. That is this line right here. And the simplest way to do this one, it goes through the origin. And then because it has a -1 slope, it's going to be 1, -1, 1, -1, 2, -2, etc. to draw that line. And this one, we would use the intercepts. So if we let x equal to 0, minus y is equal to -6, which means y equals 6. And if we let y equal to 0, then 3x is equal to -2. And then, of course, you draw the line. Now we have to figure out which side of the lines to shade on. So we're going to pick a test point and test both of the lines. Now, for the second equation, we can use the origin. And if we plug the origin into the second equation, we find out that it does satisfy the inequality, and so we would shade underneath that line. On the other hand, in the first equation, both intercepts are the origin. So I'm going to pick a different point that I know is somewhere off the line. And if I put in x equals 1, then I'm going to determine x equals 1, y equals 0. Then I'm going to determine that that does satisfy that first inequality. And so I'm going to shade above the line in that case. So again, you're just basically doing two separate problems, but adding them on top of each other. Now, because it's an and condition, you want to specify the region where the inequality shaded regions overlap. And so that would be here in this corner. Essentially, anytime you draw two lines like this, you're going to be dividing up the space into 4 sections. And so one of them will have none of the inequalities satisfied. 2 of them will have one of the inequalities, but not the other one satisfied. And then one of them will have both inequalities satisfied. As I said, for the and conditions, that's generally what we assume. We want where both inequalities are overlapping. Now, the only way that we can really represent this is to draw the graph and kind of point at it. So on your paper, you would want to indicate that this is the region that satisfies that system of inequalities. Now, you can also do these in your calculator, following the same steps that we did for the individual inequalities. You would simply graph both of them at the same time. And when you do that, again, it's going to draw both the lines and it will shade on top of it. Now, one thing that I would just caution about using the calculator is 2 inequalities aren't too bad. 3 inequalities is starting to push it. And if you have to do 4 inequalities, it's going to be very difficult to discern exactly what region on the calculator are all of the inequalities satisfied. Really, 2 is about as far as you could go without things starting to look very difficult to interpret on the calculator. So just do be aware of that as you're doing these problems. Now, if we have 4 inequalities, again, things can become quite difficult to do in the calculator. Here, 2 of the inequalities are just the constant examples, and this is typical in linear programming problems where you're trying to optimize some function relative to some constraints. And the constraints are typically going to be these lines, but in business examples, you also want all of the x and y values to be positive. So one thing that you can do for these 2 inequalities in your calculator is to just only graph the first quadrant. So make sure that your window minimums are at 0 in both x and y. And so then you won't have to worry about these other sections of the graph, and you'll just be able to zoom in on the region that is also being satisfied by these 2 additional inequalities. Now, again, the general procedure is for graphing them by hand. You always graph each line separately. So x plus 4y equals 4. We're going to graph that. And then that's going to give us this blue line right here. And then 2x plus 3y equals 6. That's going to give us this line right here. And then x is equal to 0, y equal to 0. Now, as I said, these 2 are basically just going to restrict us to this corner of the graph because that's where x and y are both positive. And so we're looking for the section of the graph that has all of these inequalities satisfied. Now, for these application problems, you will tend to graph sort of below the line. So in this red line, we're going to graph below that line, and the blue line, we're also going to graph below that line. And so the region that is being satisfied is going to be this little section right in there. Right in there. Now, again, you can do this on your calculator, but as I suggested, in order to satisfy the x and y greater than or equal to 0, set your minimums equal to 0 so that you're only looking at that first quadrant, and then put your inequalities, solve for y, put them in your calculator. Again, you'll graph, in most of these example problems, you'll graph below the line, especially if they're related to a real world optimization problem. And then when you go ahead and hit graph, then the graph on your calculator will look like this. And so it is consistent with that graph that we saw earlier. Now, in the case of an OR situation, the thing that differs in an OR situation from an AND situation is that we want any region that is satisfying either of these inequalities. So if we're looking at our graph, and again, this is the same graph that we had before, we want to include in our solution any region that has some shading. So the only section would be this one out here that does not satisfy the solution. All of the other 3 sections that have any shading at all would satisfy the solution. So again, the procedure is identical up until that very last step where you are specifying which region satisfies the system of inequalities.